Hello Shipra.
Hello, ma'am.
Can you help me in completing this pyramid?
Yes, ma'am.
Let's see. Well, that's right. Now, how many blocks have you used here?
Well, 28.
That's right. Now, suppose I start with a pyramid whose baseline has 10 blocks in it. How many blocks do you think I'll require to complete the pyramid?
I'll just try to make one and find out.
Well, that's one way. But now since we've been discussing arithmetic progressions and of course geometric progressions, I think we will be able to be a little wiser in understanding that this pyramid, which had 7 blocks to start with, has number of blocks as 7 and then in the next row 6, 5, 4, 3, 2 and 1, which is nothing but an arithmetic progression. And therefore, the total number of blocks required will be the sum of the total series, and therefore, it is going to be n by 2 into a plus l, since we know the last number as 1, and therefore, you will get the total number of blocks as 28. Exactly that is done if I start with any pyramid whose baseline contains n blocks. The number of total blocks required will be nothing but 1, 2, 3 up to n, and that means the total number of blocks required will be nothing but the n by 2 into a plus l, that is 1 plus n. And that is what we are going to learn and make use of today. What you have just discovered is nothing but the sum of the first n natural numbers. And so, if I go back to the question I asked you, if I start with 10 blocks in the baseline, the total number of blocks will be nothing but 10 by 2 into 10 plus 1, and that is nothing but same as 55. And so, this is one use of a simple relation. The sum of first n natural numbers is equal to n into n plus 1 by 2. We express that as sigma of k, where k varies from 1 to n, is equal to n into n plus 1 by 2. This is our first special result which we'll be using today and also in our next lesson. Now, this result is very easy to derive once you know what an arithmetic progression is and how to find sum of n terms of an arithmetic progression. But at the same time, there are many non-routine proofs available for this result. I would like to share one of them with you. The result that I am going to discuss right now is on the basis of what we call as counting unit squares. What does it mean and how it helps? Let us take a look at this figure. We have a figure here, as you can see. It is a kind of a rectangular arrangement of unit squares. Here, the number 1 is represented by this square of unit area placed at the corner A. Number 2 will be represented by 2 squares of unit area, here shaded in red, placed alongside AB and AC. Similarly, number 3 you can take and represented by 3 unit squares, here shaded in green. You can go on representing the numbers 3, 4, 5, etc. till the number n is represented by n squares of unit area. Here, suppose these are the squares whose diagonals will lie along the side BC. Now, we are interested in adding, calculating 1 plus 2 plus 3 up to n, and as you can see now, the total sum will be equal to the area of this entire figure, and that is nothing but area of the triangle ABC plus half the area of n unit squares. Can you see here? These are the portions which are not included in the triangle ABC. And so, area of triangle ABC plus half area of n unit squares will give us this sum. Let's take a look at this quantity now. What you have here is 1 plus 2 plus 3 up to n is equal to area of the triangle, which is half base into height. The base has n unit squares, that is your AC and AB both have n unit squares, so n into n, plus half the area of n unit squares means n into 1. Unit squares means they have side of 1 unit each, and therefore what you get is nothing but n square by 2 plus n by 2, and that is nothing but n into n plus 1 by 2. The same result which you could calculate otherwise also as mentioned earlier. So, the result is the same, but the proof is non-routine as I said, but interesting also. Next, before we move on to any applications today, we have one more result which gives us how to find the sum of the squares of first n natural numbers. Let's note down the result first. The sum of squares of first n natural numbers, that is 1 square plus 2 square plus 3 square up to n square, is nothing but n into n plus 1 into 2n plus 1 by 6. You have to make an effort to learn the result. You are going to use it in number of problems. But before that, why do we have this result? How is it proved? The proof depends on knowing a certain simple algebraic identity. Consider x cube minus x minus 1 whole cube. As you can see, on simplification it will give you 3x square minus 3x plus 1. I called it an algebraic identity because it is true for all the values of x. I am sure you will agree with me. To get our series, what we will do is we will start with different values of x ranging from 1 to n. And so, by taking x is equal to 1, and since this result is true for it, I will have 1 cube minus 0 cube is equal to 3 into 1 square minus 3 into 1 plus 1. Do not simplify this, let us keep it as it is. Putting x is equal to 2, you will get 2 cube minus 1 cube is equal to 3 into 2 square minus 3 into 2 plus 1 again as it is. Similarly, x is equal to 3 will give you 3 cube minus 2 cube is equal to 3 into 3 square minus 3 into 3 plus 1. This can go on till we take the value of x as say n minus 1, and therefore you will have n minus 1 whole cube minus n minus 2 whole cube is equal to 3 into n minus 1 whole square minus 3 into n minus 1 plus 1. The result is also true for x is equal to n. That is the number which is going to end our this mechanical process. Let us take x is equal to n, and therefore you will have n cube minus n minus 1 whole cube is equal to 3 into n square minus 3 into n plus 1. Now, why have we done this? Simply because we are interested in calculating 1 square plus 2 square plus 3 square up to n square. And if you observe what I have written here, you will see the presence of 1 square, 2 square, 3 square up to n square, but they are all separate expressions. So, to get that sum, I will add all these equations column wise, so that we are able to group together 1 square plus 2 square up to n square, and rest of the things also make a difference. Let us observe the left hand side here. When you add all of them, do you see 1 cube and minus 1 cube gets cancelled, 2 cube will get cancelled with minus 2 cube, n minus 1 whole cube will get cancelled with n minus 1 whole cube here, and so if I add all the equations, I will get adding column wise, as I said, we will get on the left hand side we are left with n cube minus 0 cube, which is not actually contributing anything to it. Right hand side it will give you 3 into 1 square plus 2 square up to n square, and minus 3 into 1 plus 2 plus n, adding the second terms of the column, and then 1 added n times 1 plus 1 up to 1 again. What you can see here is that the right hand side is giving us that quantity which we are interested in evaluating, plus it involves 1 plus 2 up to n, which I am sure now you know what its value is. We just started with that result and its value is n into n plus 1 by 2, whereas 1 added n times is easily understood to be as n, and therefore I can write 3 times of 1 square plus 2 square up to n square separated on one side to be equal to n cube plus 3 times of sigma of k, where k varies from 1 to n, minus n, 1 added n times. And so from here we can write 3 times of sigma k square, 1 square plus 2 square etc. can be written as sigma k square, where k varies from 1 to n, and is equal to n cube plus 3 into n plus 1 by 2 minus n. This can be simplified by taking n common, and you are left with n square plus 3 into n plus 1 by 2 minus 1. And as you simplify further, you can see it is going to be 2n square plus 3n plus 3 minus 2 by 2, which is clearly n into 2n square plus 3n plus 1 by 2. The numerator here can be easily factorized to n into n plus 1 into 2n plus 1. And so I can go back to sigma k square and free it from 3, and therefore we have our result proved. Sigma k square from k varying from 1 to n is equal to n into n plus 1 into 2n plus 1 by 3 into 2, which gives us 6. The proof is tedious in terms of its simplification, and you have to remember the starting identity. We are going to consider its use in finding some of certain special series, but right now let us see if we can put it to use to find how many squares are there in a figure like this. So Shipra, see this figure and see if you can find this number of squares here.
Yes, ma'am. When I come across such problems, I always miss a few and end up with the wrong answer.
Well, that is quite possible because there are so many squares in this present figure. To understand why and how we get the right answer, let us take a look at a number of such figures. To start with, there is only one square present here. So automatically the answer is 1. In this figure, where you have taken two lines which are dividing vertically or horizontally both, the figure in two equal parts each, you can see the number of squares present is going to be 1, 2, 3, 4, the small ones, original as 5, and therefore the total number of squares present is 5 only. This 5 can always be thought of as 1 square plus 2 square. In the third figure, as you can see, these two vertical lines divide this square into 3 equal parts. Therefore, I should be able to see whether the total number of squares is going to be 1 square plus 2 square plus 3 square. Just make an effort and see, you're going to get 3, 3 and 3, that is 9 squares, small squares, 1 large square, and then yes, this is the next 11th and then 12th, 13th and a 14th. This is what you get if you simply take 1 square plus 2 square plus 3 square. Now with the help of formula, right now you can also calculate it directly to be equal to 14. So if you have large values, you can use our formula which we have just derived. And so Shipra, can we go back to our figure and can you decide how many squares are going to be?
Yes, ma'am. It is the sum of the squares of first 4 natural numbers, that is 30.
Okay, so you've got the answer pretty quick. 1 square plus 2 square plus 3 square plus 4 square should be the answer. But you don't have to simplify all of them. You can use the result n into n plus 1 into 2n plus 1. So it's 2 into 4 and that will give you as 8 plus 1 9 by 6. And as you said, as on simplification, it will give you 30 as the total number of squares present in the figure without actually making an effort to count all the little and the big ones. That was an interesting application I thought I should share with you. But we have, of course, special series to consider. But before we take problems, we have one more result. It says sum of cubes of first n natural numbers, that is 1 cube plus 2 cube plus 3 cube up to n cube, is given as n into n plus 1 by 2 whole square. A result again very important and easy to apply, but its proof again depends on starting with an algebraic identity. This time we will consider x to the power 4 minus x minus 1 to the power 4, and on simplification it does give you 4x cube minus 6x square plus 4x minus 1. What you can do is repeat almost the same procedure as we have done in the sum of the squares. Starting with x is equal to 1, it will give you 1 to the power 4 minus 0 to the power 4 is equal to 4 into 1 cube minus 6 into 1 square plus 4 into 1 minus 1. X is equal to 2 will give you 2 to the power 4 minus 1 to the power 4 is equal to 4 into 2 cube minus 6 into 2 square plus 4 into 2 minus 1. Similarly, x is equal to 3 will give you 3 to the power 4 minus, and as you substitute there, 2 to the power 4 is equal to 4 into 3 cube minus 6 into 3 square plus 4 into 3 minus 1. Keep going on till you take x is equal to n minus 1, and you will have n minus 1 to the power 4 minus n minus 2 to the power 4 is equal to, mechanically replace x by n minus 1 minus 6 into n minus 1 whole square plus 4 into n minus 1 plus minus 1. Last, that is x is equal to n will give you n to the power 4 minus n minus 1 to the power 4 is equal to 4 into n cube minus 6n square plus 4n minus 1. The purpose is again the same. As you add column wise, and as you could see, you are going to get 1 cube plus 2 cube plus up to n cube. Along with that, you will also get 1 square plus 2 square up to n square and 1 plus 2 plus up to n. So we are going to put into use both the results derived earlier to get the present one. Left hand side, as you can observe, on adding 1 to the power 4 will get cancelled with minus 1 to the power 4, 2 to the power 4 gets cancelled with minus 2 to the power 4, and so on. And that will leave you with, on adding column wise, only n to the power 4 on the left hand side, and the right hand side will be 4 into 1 cube plus 2 cube up to n cube. The second term minus 6 into 1 square plus 2 square up to n square plus 4 into 1 plus 2 up to n, and 1 added n times I am writing directly now as n. Now what is left is substitution of the results derived earlier. From here you can see this is same as writing 4 times sigma k cube, where k varies from 1 to n, is equal to n to the power 4 plus, taking this term to the left hand side, 6 times sigma k square, k varies from 1 to n, minus 4 sigma k, k varies from 1 to n, plus n. This just needs to be replaced by the results. Can you give us the result now here, Shipra?
Yes, ma'am.
Sigma k square was same as n into n plus 1 into 2n plus 1 by 6 minus 4 into n plus 1 by 2 and that n as it is. This needs to be simplified, n can be taken out, and I would like you to finish it up on your own and see if you do get sigma k cube as k varies from 1 to n to be equal to n into n plus 1 by 2 whole square. 4 is already there on the left hand side, so denominator will be no problem. You just have to group the terms so that the numerator appears as this. These three are very important results, so we will take a quick look at all of them before we start with their applications. What we have proved today are sum of the first n natural numbers, which I have been using as summation k varies from 1 to n, is going to be same as n into n plus 1 by 2. Sigma k square or 1 square plus 2 square up to n square is n into n plus 1 into 2n plus 1 by 6. Sigma k cube, the sum of the cubes of the first n natural numbers, is n into n plus 1 by 2 whole square. There is a similarity, a relation here, but a whole square is what you have to remember. What we are going to do is now use these relations to find sum of certain series to n terms. If you remember, Sn is nothing but T1 plus T2 up to Tn. And so I can put it in a nutshell and say Sn is equal to sigma Tk, k varies from 1 to n. You will find that this is one way of expressing Sn, but at the same time, if you write your sigma Tk, k varies from 1 to n, only as sigma Tn, it is understood that you are adding the terms where n changes its value from 1 to n. So, we will be using alternately, whichever you find convenient to use, you are free to do, but this is a more common form. Sn is therefore equal to sigma Tn, and therefore, you do not have to write everything in terms of k. Now, what it means is, suppose I am given Tn to be equal to n square plus 2n. Can we find sum of that particular series? Let us try. Sn, as I just said, is sigma Tn, or since it is our first question, let me write it as sigma Tk, where k varies from 1 to n. And therefore, it will be same as writing sigma, where n is can be replaced by k. So, it is k square plus 2k, where k varies from 1 to n. Since addition is distributive, I can take the sigma inside the bracket and write Sn to be same as sigma k square, k varies from 1 to n, plus sigma 2k, k varies from 1 to n. Can you give me the value of sigma k square as k varies from 1 to n?
Yes, ma'am. N
Into
n plus 1
right
into 2 n plus 1 upon 6.
upon 6. Here it is sigma of 2k 2 is a constant, and so it can be taken outside the summation. So it's actually twice sigma of k. Do we know its value?
Yes, ma'am. 2n
2 is already there. Sigma k is n
into
yes,
n plus 1
right,
upon 2.
upon 2. What's left is just basic simplification. You may take n into n plus 1 out, and you are left with 2n plus 1 by 6 plus 1, and that can be written as n into n plus 1 into 2n plus 7 by 6. This is the sum of that particular series whose nth term is n square plus 2n. We are asked to find sum of n terms of a particular series whose nth term is given as n cube minus 2 to the power n. So, if we go back to the idea that Sn is sigma Tk, k varies from 1 to n. It will be same as sigma k cube minus 2 to the power k, right? And that will be same as sigma of k cube minus sigma of 2 to the power k. K varies from 1 to n in both the summation. Can you tell me the value of the first term here?
Yes, ma'am. This is the sum of the cubes of first n natural numbers.
That's right. And so it will be equal to n into n plus 1 by 2 whole square. And what about the second term?
I'm not too sure about this.
Okay. So let me rewrite it as it is and explain to you what the value of sigma 2 to the power k is. Sigma 2 to the power k is actually nothing but in its expanded form. As you take the value of k from 1 to n, 2 plus 2 to the power 2 plus 2 to the power 3 up to 2 to the power n. And this I am sure you will be able to relate to as a geometric progression, right?
Yes, ma'am.
With a as 2
2,
and r as
2.
2 and n terms there, therefore it will have the sum as 2 into 2 to the power n minus 1 by 2 minus 1. And so the sum of our series will be equal to, we had calculated the first term as n into n plus 1 by 2 whole square minus twice of 2 to the power n minus 1. That is what the sum looks like. And with this, we wind up our lesson for today.
Yes, ma'am.
In our next lesson, we will consider more applications of the results learned today, but do take a few direct questions on the results.
Thank
Right?
you, ma'am.
Welcome.